Okay. I I do something at Zurich Spark. I don't have a job description, so uh, okay. I do something at Zurich Spark. Mostly these days, it has been working on a lot of recursion related stuff, and in particular, that has involved working with Nova. Nova is like a pretty new, or I guess not new anymore, but about a year or two old recursion scheme. It's not exactly accurate to call it a snark scheme, but more just like a recursion slash folding scheme. So today's talk will be about Nova and all of the different ecosystem it has started, which includes Supernova and Nova Scotia. But first, to be clear, there's many Novas in crypto. So what this is not is that it is not Arbitrum Nova, which is some data availability thing I don't know about. It's also not Tornado Cash Nova, but it's slightly closer. It is Microsoft Nova. So Nova was a construction that Srinath Sethi and Abhiram from CMU, I believe, came up with about a couple of years ago. And now there's lots of many people working on it, including some EF, like VDF projects, some Filecoin work. There's also, there's lots of different people working on it. The short story is I'm someone who's working on Nova Scotia, which is something we'll get into later. I'll just get started. I guess I should say that I'm pretty... Okay, so we'll get started with recursion. I guess just first hand raise, I guess. How many people saw the blog post that we shared last night? Or are generally familiar with what recursion does or what it means to? Okay, cool. So recursion has many different use cases in Snarkland. One of the more popular use cases is incrementally verifiable computation. So what is incrementally verifiable computation? Just to repeat. So generally, incrementally verifiable computation is a structure where you have some function f, and you have some starting input, let's call it z0, and you chain this input into repeated calls of f. And additionally, you have this ability to inject some extra witness, usually it's W0 or whatever, and it can also act with f to create the next z1. But the reason it's called incrementally verifiable computation, so this is just incremental computation, right? So the reason it's called incrementally verifiable computation is that you can do this thing where you can start making some boxes around these. Let's say we call this pi1, and then we call this pi2. So you can start making these boxes around them, and what these boxes could mean, so pi1 and pi2 here could mean that this is a succinct or some proof of computation of one iteration of f. So in particular, pi1 here would mean that starting at z0, running f on this z0 with some witness w0, I get output z1. Pi2 would mean that running this twice gives you z2. And the cool part is that pi2, if you want to verify or if you want to generate a proof for pi2, you don't have to start from scratch, if that makes sense. So you don't have to run both f on z0 and then f on z1, because you can use pi1 that you created previously, and instead you just show that, okay, if I run pi1 and I get output z1, then I run f again on z1, I get z2. And pi2 is sufficient to compose these two. Right. Right. So in case of IVC, the original, I don't know, 2008 paper or whatever, it was the case. But later we'll get into something called non-uniform IVC. And then that would be the case that f would vary at each step. Yes, I forgot about that part. So the question was, is it mandatory that f will be the same in each box? And the answer was what I just said. Okay. So IVC there's many ways to instantiate IVC. And the sort of common one that we all have seen probably before is the snark-based construction. And I already like sort of gave a hint at how a snark-based construction would look. But let's just like, fully flesh this out. So I'm going to draw this box and I'm going to call it modded f dash. And what it will be is like it will have in itself the function f, and it'll have a snark verifier. And so this inputs, so we're drawing some, arbitrary I, what this box looks like. So it inputs zi minus 1, which was the previous output. The f function outputs zi, and then the snark verifier itself inputs whatever proof we had from the previous one, which would be pi I minus 1. And let's see, so together, this would yield pi I. Does that idea sort of make sense? So what we ended up doing is that to very much fully instantiate what pi are, we say that pi's are different snarks, or the same snark, but different instances of the same snark. And inside of pi I would have a snark verifier. So, if you instantiate with this CROT16, you would have like a pairing check. Or if you do snark, you would have like fry or whatever else it is. And this is a pretty like sort of popular way to do recursion or incrementally verifiable computation. And for instance, Polygon zk-EVM does almost exactly this with snarks. So this snark verifier is the sort of extra piece that you have added onto your like starting point f, right? And usually this piece is described as the recursion overhead of this particular scheme. So if you were to put like a pairing check here or something, pairing checks are very expensive inside of a snark, so that would have a huge recursion overhead. But if you put, for instance, hashes or something, it might have lower overhead. So I've been setting all of this up because, right, so the question was, what is the input and how do you carry them along this repeated compute? So the answer is, so you have zi minus 1, which is proven by pi I minus 1. So it is proven by pi I minus 1 that running I minus 1 instances gives you zi minus 1. And then you show additionally that running f on zi minus 1 gives you zi. So if you compose these together, you get this pi I thing. Does that answer? Right. So if you so the question was, do you actually need to carry pi? So if you just carry, right, and the intermediate inputs. So the answer is, so one way, or the sort of paradigm we're assuming ourselves in is this IVC paradigm. And in IVC, basically the idea is that we want to be able to slowly add stuff to like a existing proof, if that makes sense. So one way could be that, these proofs are just like fully unrolled, like n iterations of whatever this function is, right? But that would be like, if n goes larger and larger, that becomes worse and worse. Right. So Richard just gave a summary of what basically we just talked about, and the like sort of to like reiterate what the idea is that, so you have this box of modded f dash, and this is like a regular function or whatever, right? So you can code this in your R1CS or Blanc or whatever constraint system, and then use it to generate pi I. So pi I is a proof of running f dash. And what does f dash itself prove? It proves that running one iteration of f and running like a verifier on the previous I steps. Right. So in practice, you could. So the question was, how do you initialize, or how do you start making this chain of proof? And the answer is, in practice, usually the simplest way is to add like a if condition to your snark verifier, which just says, oh, if I is equal to 0, accept nothing. So this is the idea here is that, if you have some function that you can express as constraints or something, you can, do whatever you want with it. So you could have if conditionals, or you could have like the previous n inputs as is inputted, or you could have a snark verifier, which would be efficient for some reasons. Right, WIs are just, or the question was, do you also have WI plus 1 for the next step? And the answer is, so WIs are just injected at each step. There is no like statement being made about WIs in this process. So the question was, what's the size of the input and the output? Right, and what is the comparison of the size? So typically in a start-based system, you would want that pi i's in particular remain constant size or don't grow faster than like order n, if n is the size of your compute. So at least you're getting some efficiency gain out of it. The sizes of zi and wi and all of these things, we don't make any claims about. It is up to the function f to decide what these are. Sounds good? Okay, so yeah, this was some amount of setup that people must have or might have seen before. But the point of this setup was that essentially Nova you can look at in many ways, and one of the like most satisfying way to look at it is as a machinery that can allow you to do IVC. And the like next roughly next 30 to 45 minutes will be us going through how to get to IVC, and later with Supernova and IVC. And we'll start with something really basic, BLS signatures. We'll figure out how to get to like some function aggregation things. Then we'll figure out how to add chaining to these function aggregation things. And finally, we'll hopefully get to Supernova. Right. So this is a quick recap on BLS signatures, or more particularly, what the thing we care about is homomorphic commitments. But BLS signatures is like a good example of where it shows up in production and people might have seen before. So the way BLS signatures work, you have this keys and signature and verifying algorithm or whatever, but the key part is the verification is some pairing check. And in particular, it's that pairing check up there, or I should have it here. So it's this pairing check up here. And this pairing check says that if given a signature, the generator of this group, this should be equal to the public key multiplied by the hash of the message. So this is roughly what the verification looks like. And it turns out that because this is a homomorphic commitment scheme, you can, or not commitment scheme, but like pairing groups are homomorphic, you can do this thing where you can aggregate many signatures from different public keys. And the way you do that is that instead of you replace this public key by a multiplication of all the public keys that would have signed something, you multiply this by the hash of the message, or exponentiate with the hash of the message. And on the other end, you check if whatever signature you get is accurate. And this could not have been created unless you had all the starting point signatures of each individual one. So the key takeaway here is just that you have this sort of ability to take you almost have this like bag of signatures, and you are able to say that let's take some of the things in this and make one claim, and that is able to sufficiently check that I had everything in that bag. So we started with n of these signatures in this case, and we composed it into one pairing check. So similarly, the sort of next step, the next step I'll suggest is that if we were able to do this with any general function, we would be able to make some interesting things. And the interesting thing in particular will be that we would be able to say that, oh yeah, I have many runs of this function, and I am able to show that all of them are correct by just showing you one thing. And like you can already kind of see why IVC and this are very related problems, but we'll just like sort of suspend disbelief for now that this will somehow relate back to IVC. Okay, so let's start with dot products as the interesting sort of very simple starting point. So in particular, the thing we will start with is going to be, let's say I have some matrix A that we agree upon. And we'll also pull up this here. Yeah. So let's say I have some matrix A, both prover and verifier agree upon, and what I want to show is that A dot Z1, where Z1 is some vector, is equal to, let's say, a bunch of ones. And also I want to show A dot Z2 is, satisfies the same relationship of a bunch of ones. Right? So this is what the prover wants to do. And he wants to convince the verifier about this statement. So how would he do that? So there's one very nice trick that a lot of people might have seen before in like ZK AVM circuits or Plonk, or I don't know, it like shows up everywhere. So the trick is this idea of random linear combination. The rough idea of this trick is that if you have some random values and you have many, let's say you have many values and you have some random source, then you can compose these values together with this random source, and no one can, I guess, do some like back propagation from this. I guess I'm saying back propagation, but really what I mean is that if you have the output of this random source times a bunch of values, you're not able to make any claims about this starting with just the values themselves. And in particular, in this case, what we'll do is we'll say, let's say we have some Z3, which is equal to Z1 plus randomization times C2. So this R is some random field element that the prover cannot predict in advance. And then what is true is that A dot Z3 is equal to, R plus 1, and so on and so forth. And you can already see why this is, but just to expand, which is A Z1 plus R A Z2. So because of this second relationship, it is true that A dot Z3 is equal to R plus 1 repeated many, many times. So if I can just convince the verifier of this fact, I'll be done, right? So how can I do this? So the simplest way is, we just give the entirety of Z3, the entirety of Z1, the entirety of Z2 to this verifier. The verifier comes up with some random number, or comes up with this random R, gives it back to the prover, which the prover uses to generate Z3. Prover gives back the Z3 to verifier. We check this relationship. We check A dot Z3 is what we expected it to be. And then, you're done. Wait. But this is not very helpful because now you just like send the entire vectors across. So like, who cares, right? So the thing you actually do is that you insert some step at the beginning, which is you generate Z1 bar, let's call it, which is some commitment of Z1. And similarly, you generate some Z2 bar, which is also a commitment. You send these commitments over to the verifier. The verifier generates this whatever random challenge based on these commitments, sends back this R. You generate the Z3 as a prover, and then you also insert one more step here, which is generation of Z3 bar. And Z3 bar, again, is commitment of Z3. You send back Z3 bar. Verifier checks, Z3 bar is equal to Z1 bar plus R Z2 bar. And so why is the verifier able to do this step? Oh, let me undo that. So why is the verifier able to run this step? That's because we started with this primitive of homomorphic commitments, or additively homomorphic commitments. And given two commitments, taking some scalar multiplication plus addition of these commitments still gives you whatever the commitment value world of the Z3 bar was supposed to be. So to be very specific, it is the case now that Z3 bar corresponds to what the commitment of Z3 should have been, and the prover cannot forge a Z3 given a Z3 bar. So now you're able to, so the verifier in particular is able to do this A dot Z3 bar is equal to, R plus 1, this repeated check. almost trivially, right? And on the other end, now what did we save by doing this commitment exercise? Is that now the verifier only had to look at the commitments of the vector z1, z2, and z3, which were like order 1 size. So now you've generated like almost a succinct proof for showing dot products. A was another vector. Yeah, and then it's just like A is previously agreed upon, so you're able to do scalar mul. Yeah. The question was what is A, and that was the answer. Sorry. Okay. Cool. So this is a very simple example, but I hope you should already be able to see like the parallel with like BLS or those kinds of things. Now we have this this very simple function of dot products that we're able to almost take many of these. We have like a bag of these, Z1, Z2 up to Zn. We're able to convert these into just like one proof, convince the verifier that everything in this bag was correct by just showing them this one sort of aggregate proof. So now dot products are not sufficient to do anything interesting. So we'll have to step it up a little bit, so there's many. So the question was from Barry, why are dot products not interesting enough to do something of utility? Let's see. Usually the way we think of, I guess, snarks and stuff, it's you need at least the ability to do addition and multiplication. And that's because without this, you cannot cover NP. And NP is like the class of problems where you can do verifications in polynomial time. With just addition, you're only able to make statements that are, I guess, not sufficient to do all of NP stuff. Is that a reasonable explanation? Do you have something better? Right. Yeah. Turing complete is another way to put it. So everything in NP is Turing complete. Cool. Yeah. So to get Turing completeness now, and to get to all of NP, we'll go to this sort of common constraint system that we see called R1CS, which stands for rank 1 constraint system, and has something to do with matrices that I don't fully know why rank 1 is the name for it. But the sort of rough idea of R1CS is that you have relationships of the format AZ, Hadamard BZ is equal to CZ. And when I say Hadamard, it just means I'm doing element-wise multiplication. So Z is some witness vector, let's say. A is some square matrix. You take whatever dot product of these two, get a new vector out. Same with BZ, you get a vector. Same with CZ, you get a vector. And now with just these vector, you do like element-wise multiplication, and then you check if it's equal to that exact element in CZ. So this is the relationship that R1CS describes. And if we could do this exact same thing that we have been doing before for dot products, which was take 2 of these or n of these and convert that into just one proof, will be sort of done, right? Yeah. All right. In particular, the thing we want to achieve is that, let's say this is Z1, 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 and then you have some Z2, Z2, CZ2. So now the prover wants to convince or show both of these to a verifier, and let me write down prover, verifier. So the natural idea would be that, can we do the same kind of like random linear combination thing that we did before? And same way, let's write up Z3 is equal to Z1 plus R times Z2, assuming, we can get some randomness R somehow. But then, so now we start plugging stuff back in to this like A business, and that looks like AC3, BZ3, CZ3. Or this is at least the hope that you would have some version that would look like this. But I won't go into too much detail of what the math works out to. But you can just believe me that when you try to put Z3 in here, it ends up being that you end up with cross terms. And what I mean by that in particular is that you end up with some terms that look like some value from z1 plus r z2 plus, or let me just not do r. I'll just do z1, z2 times some combinations of a, b, and c, which we'll just call them e for now. So the thing that will happen is that you would have both z1 and z2 in your folded version. And this is very problematic for many reasons, because now your proof has to have more data than what is necessary. And so there's this, you can definitely do it, and it is almost exactly what you do. But the sort of more convenient thing to do is that we'll just define a slightly better notion than R1CS. And that in particular is this idea called relaxed R1CS. And the only difference between a normal R1CS, so the question was, what do I mean by you can do it? So the particular thing I mean is that relaxed R1CS is a superset of R1CS. So any R1CS relationship is a relaxed R1CS relationship. So anything that you can express in R1CS, or any of this math that I'm about to show you, can still work out almost exactly the same way for R1CS. You'll just have to book track a lot more variables, and it would just be annoying. And you would basically end up with book tracking the exact same variables that relaxed R1CS does. Right. So the question was, we have relaxed R1CS, which is slightly unfamiliar. So can we just work with R1CS and do the exact same thing? Right. So the answer to this is that relaxed R1CS is actually R1CS, because relaxed R1CS is NP, and all of these things are in different ways to express things in NP. So in particular, there exists a way to take any relaxed R1CS and convert it to R1CS with not more than a constant overhead, I believe. So anything you're doing in R1CS land is the same in relaxed R1CS land. So in particular, the thing that would happen if you try to do this with R1CS is that you'd end up with the exact same variables, and you'd just be like, oh yeah, this is back to relaxed R1CS. So the question was, or the summary from Barry was, so we start with R1CS, we try to do this folding thing that we've been talking about, and it is almost the case that we end up with relaxed R1CS. And yes, that's accurate. So that is almost exactly what happens. And in particular, the reason this needs to happen in a more formalized way is that we're going to chain many of these later. And when we start chaining, it will be very annoying to book track, oh, one of these is R1CS and the other one's relaxed R1CS. Oh, I guess essentially I'm thinking that, or the question was, what do I mean by book track? The particular thing I mean is that later we'll get to some IBC land, and we'll have many of these R1CS and relaxed R1CS instances. And we'll have to figure out a way, okay, one of these is R1CS, the other is relaxed R1CS. How do I combine these together into one, right? The other version could be, oh, I have one relaxed R1CS, I have another relaxed R1CS. How do I combine these into one? So just to simplify all of that, I'm just going to say, okay, everything's relaxed R1CS. I just need to figure out a way to combine relaxed R1CS instead of individually R1CS or all pairs of these possibilities. Right. The question was, do I see any way where the cross-term stuff can be helpful? So the complexity theoretic answer is there shouldn't be more than constant helpfulness we can get from the cross-terms, because both are NP, and you can do more powerful things from a complexity theoretic standpoint. Although that said, in practical cases, it definitely could be the case that you find some optimizations of for instance, maybe there's some way to shove a lookup into one of these cross terms, right? And it's yeah, it's not complexity theoretically more powerful, but it's very helpful if you want to run a zk-VM, right? Yeah. Okay, cool. So let's get started with relaxed R1CS folding. Also, let me quickly time check. Okay. So let's get started with relaxed R1CS folding. So in case of relaxed R1CS, the main diff from R1CS is that we've added this new term U and this term E. So the paper calls E the error term. I really hate that word because it creates a lot of confusion for many reasons. But just imagine that E is some conduit for the cross terms, and U is some conduit for squared terms, if that makes sense. So squared terms, I mean that you have some, when we were trying to do this before, we would have like some terms that look like Z1 square and Z2 square, and those get sort of like converted into this U value. And we would have some terms that are Z1 times Z2 times something, and those would get converted into the E stuff. If you really care, you should look at the paper, and they explain how you exactly get to U and Z. Okay. So now we get to like the same sort of like simple toy scheme that we had, and like the same kind of problem we're trying to solve. So in particular, the thing we're trying to do is that the prover has two instances of the Z's, essentially. And in particular, they are this E vector, or E1 and W1. I've just called it W1 to absorb U as well into it. And similarly, you have E2 and W2. And on the verifier side, they have some commitments to these. So in particular, they have a commitment to E1, they have a commitment to E2, they have a commitment to W1, W2, as well as they have whatever public inputs the like snark had, or I shouldn't say snark, the R1CS relationship had, and they also have whatever use the prover claimed to have. So the prover also has all of these things because the prover is the one committing to giving these to verifier. So the question was, are E and U vectors of the same size? So the question was, are U and E here vectors of the same size? And I believe it has to be the case that E is a vector of the same size, but for U, I am not so sure. I suspect it does not, it's just some square matrix. But it will be the square matrix on the same size as C. Right. But yeah, we can double check afterwards. Huh? Oh, interesting. Okay, yeah. So we've just learned that the paper says that U is actually just a scalar element, and not even a matrix. Cool. Any other questions? Cool. Yeah, so okay, back to our sort of like toy scheme that we started with. The prover wants to convince that he is able to take E1 W1, E2 W2, and convert them to some new values, E and W in particular, which are the folded version or the folded check of both E1 W1 and E2 W2. So in particular, this is doing the same kind of thing. We had a bag. We took two of the relationships that we knew were true, and we converted them to one of these same kind of relationships. And this in particular is also the general definition of a folding scheme. So the ability of a folding scheme is to take two relationships or n relationships of the same kind and convert them to one relationship of that same kind. And as long as this one verifies, all of them will be correct. And this is also the exact same thing that was happening in BLS or our previous toy example. Cool. So what does this interaction between prover and verifier look like? The prover, computes this value t, which is like described here, but I'll just ignore it almost. And this is just doing whatever is necessary to compute and like keep track of E and the U cross terms. So you commit to this t. Send it over to this verifier. The verifier again computes a random challenge, gives it back to the prover. The prover does the random linear combination thing, and they end up with E and W, which is the like the new vectors that correspond to both E1 W1 and E2 W2. On the verifier's end, the verifier will be convinced that this E and W was created honestly if they are able to do these checks. And in particular, these checks are just the same checks or just the same relationships, but on the commitment versions. So because we are working with or additively homomorphic commitments, where the verifier is able to verify that whatever relationship the prover claims that these new E and W hold will also hold true in case of the commitments. So in particular, the verifier ends up with the commitments of both E and W and U and X, and the prover ends up with the new folded E and W. So the question was, does T prevent taking an invalid proof and then chaining it with valid proofs? And the answer is yes. So if you start with just, like you sequentially start with n of these, let's say, and you keep adding one more, and at each step, you're running these set of checks, then committing to T and getting the randomness would prevent that in like the random Oracle model. Right. So this was what we were trying to like get started with before, right? Or the question was, you provided a summary and you're trying to verify if the summary is correct. And the answer is that this is exactly what we were trying to do in the previous like slide, where we had Z1 plus R times Z2 kind of structure, and we ended up with this relaxed R1CS thing. Yeah. Cool. So now, like looking back at our progress meter, we started with just homomorphic commitments, or just an idea of how we could. Right. So the question was, is there a way? So if we work in a world where we have more than 2 instances or many instances, can we batch together the checks on or creation of all of these things? Of all of these things. And the rough answer is, I believe, yes. So if you commit to all of the things or all of the instances before, right, then you can get a new random challenge, and then you do like a polynomial thing on this, right? And then you're able to do some amount of batching. Obviously, you still are computing like a polynomial instead of like just like A plus R times something. So the question was, is there a world where we can start taking 3 or 4 or n of these R1CSs, combine them together, and does that give us any advantage over the current paradigm? And the rough answer is, I believe not, because it would end up being the same. Like asymptotics, it would end up being the same. It might be the case that you get some like mileage out of like, oh yeah, this is like faster to compute on hardware or something, that kind of thing. So now, so I guess we were looking at our progress meter. So this is our paths to supernova, and now we've gotten to the step where we have this primitive of folding schemes. We're able to take 2 of these, combine them into one of these checks. But we still haven't gotten to like full IVC. Or in particular, the thing we haven't gotten to is that proving that I'm chaining the inputs from the previous step to the next step, this kind of setup. And then later we'll get more deep into like this NIVC thing. So the next step is, we figure out how to add some way of chaining things. And in particular, we'll do the same kind of setup as we did with our snark verifier. We'll come up with some modded f dash to represent repeated iterations of f as the IVC function. Cool. Right. So we have, as before, we have our f, some input zi, or so I'm going to put a folding scheme here. Oh, actually, one sec. I might have deleted. Okay, cool. Yeah. All right. Cool. So yeah, as before, we're going to construct the new modded f dash function. And this function's responsibility will be to do the chaining thing that IVC is very helpful to model. So in particular, this function will input some zi, or the f function inputs some zi, outputs some zi plus 1, and additionally it has to verify that everything before was correct. So now I'm going to use the word claim for many different things. And the word claim, I really just mean I'm going to commit to the computation. So we'll have these two variables, small ui and capital UI. I don't like this notation, but this is what the paper uses, so I'll go with it. So small ui claims that running f dash on zi minus 1, so that is just the previous instance, outputs zi. The capital UI or large UI claims that running f dash on I minus or f dash I minus 1 times on the starting input, which was z0, outputs zi minus 1. So in particular, the thing we have is that we have two statements of the same kind, almost. One of them claims that the first I minus 1 steps were correct, and then the other one claims that just the previous step was correct.
Upper part, this is correct right now. I plus 1 with pilot.
Yeah, they're correct. Oh yeah, the question was, are the indices correct in the left and right side? And they are correct, yes. Or at least I believe they're correct. If you see a bug, let me know. Okay, cool. So why are we able to do this? Right, so when I'm raising it to the, or the question, well, what does this notation mean? And the answer is that when I'm raising it to the power, I mean it's been repeatedly applied I minus 1 times to z0. Cool. Yeah, so in particular, why were we able to do this? Because, our folding scheme is like this black box almost, which is able to take... Right, so the first claim, or the question was, what do these claims mean? And the first claim meant that just the previous step was executed correctly. And the second piece, capital UI, meant that the first I minus 1 steps up to it were executed correctly. So what is happening is that, we have something that has been tracking, or in like Halo 2 split accumulation type stuff, this is called like the running instance. So you have this running instance that has been tracking up some compute up to like I minus 1 steps. And now you're going to prove that if I chain this with this just previous step, I get this new value out. Yeah. Okay. So it appears we have uncovered some confusion. So the confusion we uncovered was that so this small UI is making a claim about just the previous step and not this step. This is independent, or just the above step is independent.
Why, at least for me, then would be confusing is because if we are proving the correctness of the previous step on lowercase u, and in uppercase u, it looks like you are proving that the computation is correct from the beginning, which should also kind of include this last computation of the last step, but that's not the case. So you have everything until the last one, which is a different instance, and then you will prove the actual one, which will carries over to whatever you will. Is that the case?
Right. So I will not summarize that, but I will just say that yes. So roughly what. So I'll rephrase that. So basically, what is happening is that in this step, we're getting two things about the previous step that was claimed. One of those things is claiming something about just the previous step, and the other thing is claiming about everything before just the previous step. We're going to take these, combine them into something that claims everything just up to the previous step. And then additionally, we are going to take just this current step and run this through this modded f dash function. And what will, I think this will help. So what will happen is that we'll run this modded f dash now through our prover and get this output of that's ui plus 1. And this ui plus 1 will now claim that f dash, when executed on zi, gives output zi plus 1. So this will be this exact claim, as well as a claim of everything that happened before it. So the question was, are these UIs tracking through the slides? And the answer is no. I really dislike this notation, but this is what the paper uses. So the question was, are these commitments to UIs? And the answer is, it's a little complicated. In particular, the thing that's complicated is that I think next slide will go into much more detail about this, but roughly when I say claim, that is when I mean that we're working with commitments. And when I just say the values themselves, I mean that we're working as a prover on those values. So the one other thing that's happening here is that we're almost like mixing what a prover is doing and what a verifier is doing in this diagram. So that's the other part that's slightly confusing. So now we're going to open that box a little bit. Sounds good? Right. So the thing we're trying to do here is we're trying to use our folding scheme thing that we have created. And the folding scheme thing has this property where it can take two instances of the same kind of thing, convert them into one. So the reason I'm separating these variables, yeah, they're both tracking from the previous step, but the reason to separate them is to show that, okay, we're going to input these into our folding scheme thing, and it will spit out a new folding scheme thing. Does that provide explanation? Okay. Yeah, so to summarize that, Carlos suggested that it is the case that at all times the size of our things remains equal. And yes, this is the case, and I'll just open this box a little bit more, and there'll be much clearer why. Cool. Yeah, so I was planning not to open this box just because it gets a little more confusing, but since we're here, might as well. Okay, so the way I'll open this box is by saying that this is actually, there's two things happening here. So in all of these things, we had this notion of prover and verifier. What's actually happening is that, much like we had the snark verifier running, this is actually a folding scheme verifier that's running here. And in particular, the way this folding scheme verifier runs is that it, sort of works with this prover. So essentially what we're doing is we're taking this diagram. We had the prover and the verifier. This verifier is going to go inside of our modded f dash box. This prover will stay outside, but we'll see how it plays in. So essentially I've taken this diagram that looks like this and folded it like this way, if that makes sense, and put the verifier in the modded f dash box. Cool. So in particular, this is a folding scheme prover. And this has the same kind of randomness or transcript thing happening, as you saw in the previous slide. But the other useful thing to note here is that this also has the same inputs that this prover here, that this guy here had. So it is the case that these are also tracking some E1, W1, and in the paper they call it small E1 and small W1, but that's even more confusing. So the small E1 and W1 correspond to things of this, and this capital E1 and W1 correspond to things of this. And as an output, it spits out, I forget what they call it in paper, but essentially like some E and W, which are the same. So in particular, E1 and W1 are the E value and the W value corresponding to capital UI. And small E1 and small W1 are the E and witness values, or not witness, I should say, E and W value corresponding to small UI. Yeah, it's just like very confusing. Right. And as an output, you also, similar to before, spit out E and W, which corresponds to this UI plus 1 now. I don't know what the paper describes these. Right. We're just assuming there's like, the question was, do we need other stuff like A, B, and C? So in particular, in this case, we just started with A, B, and C sort of pre-initialized. So in this case, it is the case that F is like fixed, like long before we even started this. Prover knows this, verifier knows this, everyone knows this, common knowledge. Cool. Yeah, so does this opening the box help a little bit? We can open it more, but I would recommend we don't. Oof. Okay, all good. So if you believe me, right. Right. So when the question was a summary, and the sort of counter summary of that is yes, that is correct. And the thing is that's happening is that to make a proof, you run a folding scheme verifier inside your prover. So your modded f dash function runs a verifier for the folding scheme at ith step for the previous I-1 step. Exactly. So the summary was the verification of the proving or verification of the previous state is part of the proving state of this step. which is exactly true. And this is also what was happening in the snark verifier setting with IBC that we saw like very long ago. Yeah, this one. So this was also this case here. The verification of the previous step was the part of the prover's work in the current step. Right. So the question was, can we go through a quick mental model of how to add zero knowledge to all of this? So far we've just been working with commitments and I guess vectors themselves. So to add zero knowledge, you would to add zero knowledge to the commitments themselves, it's quite simple because in the case of we only need additive homomorphism, so you can work with Pedersen commitments, and it's quite simple to add zero knowledge to Pedersen commitments. But you also need some. There's also some more work you have to do. We can go through it after this discussion. Yes. Right. So the question was, is E and W necessary in this case? So as a prover, it is necessary to keep track of E and W. So it is the case that in the next step that we do, we will need to know the values of E and W as a prover to be able to make this next claim. Because otherwise we would only end up with commitments to these. And you can't add new values to a commitment, if that makes sense. Right. Yeah, so there's definitely a lot to digest here. I guess there is one check that zi minus 1 is equal to the output of the previous step. The question was, is there any other thing happening in this modded dash box? And that is just checking that the previous value output was the next value's input, which is one constraint. Yeah. Cool. Yeah, so far we have been working in this model where we're having sequential compute. The capital UI is almost like a running instance that we're tracking across this compute. And each time, we take the just previous step, fold it into this capital UI, next, and keep going forward and forward. But that is not very efficient because now you're stuck to this sort of single core execution. So one thing you can do with Nova is that you can parallelize the creation of this folding into a binary tree structure. And in particular, the way this works is slightly complex, but the rough idea is that here we have this f repeated, let's say 6 times. What we'll do is we'll start folding upwards instead of downwards, if that makes sense. And in particular, we'll take 2 small instances, fold them together into a longer chain. And in particular, so at this sort of base layer, we have this proof that says, oh yeah, if I input Z0, I get Z1. Right, so I'll just elaborate on what I meant by upwards and downwards, and hopefully that'll explain it. So with downwards in particular, I meant that in IBC, you have this sort of running instance of capital UI at each step that you keep folding the new UI, small UI in particular, into. Or let's just say U0, U1, and so on and so forth. And it is almost the case that you take whatever was the proof of previous step, fold it into this running instance. Take the next one, shove it into this, keep doing this again and again, right? And now in this binary tree sort of setup, what we're going to instead do is we're going to take 2 small instances of 2 small chains almost, and convert this into one proof of this longer chain. Does this make some sense? Right. Right. So that is exactly what's happening. We're going to build a tree, a binary tree of this compute. And by folding upwards, I mean we're going to combine 2 small chains into one double the size chain. Right. So the question is, why are we trying to do it this way instead? And the reason is that once we do this, we'll have no path dependency on the capital UI having to be dragged across the previous step to the next step. And it would be the case that this proof of step 1 to 2 can run in parallel with this proof of step 5 to 6. And as soon as we get this property of there's no interlocking between things, we can just parallelize this infinitely. Yes, so the question is, how can we even discover Z5 or Z6 when we haven't run the compute that far? And the answer is, so the parallelization is only for proving. We run the witness gen in sequence or however you want. And this is also, for instance, the case with how normal CPUs work or something, right? Like you can compute like this first pass almost of like, okay, what are the values I need to fill in, and then now I'll start parallelizing into a prover. Right. So the question was, are these pies different from the pies we were seeing before? And the answer is yes, and that's what we're going to get into now, in particular. But like high level, each of these pies are statements about chains of small proofs. Okay, so now let's get into it a little bit more. Right. So the question was, what is exactly or like one answer to this question would be, what is exactly the thing that is being proven in each like node of this tree? Because the sort of question was, how would you know that when you combine two? Right. So the question, just to reiterate, was when you do this folding, or I think it might be easier if you just come back to this after the next slide. Sounds good? Okay. Right. So in particular, the thing that is going to happen is that we will have at each node of this tree some proofs, or actually, let me just hide the other part. So at each step, we will have some proofs, or each node will have some proofs. And in specific, we'll define what these exact proofs mean in a lot of detail. We'll start with the sort of base case, which is like the lowest layer of this tree. And in the base case, it is the case that, so I've gone with this notation where L is like the starting point of the compute. So we'll have some proof about this function f dash from L to L plus 1. So this means that it is claiming that step L of f dash was executed correctly. And to be even more specific, it means that running f dash on z of L outputs z of L plus 1. Does this sound reasonable? Okay, cool. So what does this have to do? Like, what does this f dash have to subclaim almost? So definitely it needs to subclaim whatever R1CS was defining f, right? It needs to subclaim that running ZL on f was correctly outputting ZL plus 1. And then there's two boxes that do nothing for now, right? We'll see what these boxes will need to fill in with, right? And there's also like this input from left and right that's empty, and we'll also start filling them in for the other nodes. So this base case, I hope, makes sense. So now let's get more interesting. And also hide the prover part of this for now. So if this is an internal node, what does this have to do? It is going to be a proof of f dash from L to R, which is some range in our steps. In particular, this will claim steps L to R of f dash, which means it's saying that running f dash R minus L times on z of L outputs z of R. Everyone with me so far? Okay. So now I'm going to add one more variable to this mix, which will be h. Let's just say this will mean half for half of this range. So for the next part of this conversation, h is equal to L plus R divided by 2. So it's the center point between L and R, right? What does this f dash have to input into it? It has to input one like left child. So in particular, let's look at step 1 to 4 here. This has to input something from step 1 to 2, and it has to input something from step 3 to 4. So in this particular case, L is 1, R is 4, H is 2, or H is 3 actually. H is 3, and in particular, this has to input some f dash proof of 1 to 2, input some f dash proof of 3 to 4, and convert it into some proof of 1 to 4. Cool. So what does the left child supposedly claim? It claims that running f dash on the left half of the compute gives whatever is the value that is claimed at like the half point. So going back to this, here the claim would be whatever is like the joining point between step 1 and 2 and step 3 and 4. This value is what is claimed by ZH. Similarly, on the right-hand side, you would have the alternate claim, which would say, oh, if I run f dash on the right-hand side with some particular zh, I'll get into why there's a dash over it, outputs zr. So these don't have to be public inputs. This is a folding proof, or these are two like folded instances that we are going to verify in our f dash. Can I just quickly finish and then get back to this? So in particular, the sort of cheating like prover could do is that it could take some claim and not prove the middle step. It could just start with some random step, right? Like in particular here, you have this proof of step 1 to 2, and you have this proof of step 3 to 4. But what is combining these two things, which is also the question that was previously being asked. So one more check you have to do is to make sure that the output of the left side matches what the input of the right side was. So in particular, this is what is being claimed by this box. So that box adds that one check, which is also very similar to the IVC check that we had previously, right? And there's no R1CS here that this box has to prove. So that's just like an empty thing. So now you can compare both your base case and your internal node case and get some sense for what's happening. Okay, now I'll take more questions. Yes. Right, so Barry just nicely summarized this. I'll give my counter summary and let's see if Barry likes that. So the thing that we are trying to do here is that IVC is meaningless if it's just a bunch of things in a bag. If it's just a bunch of statements about running this F on a bunch of input, it doesn't mean anything. So the thing we need to do is we need to be able to chain these into something meaningful. And when we chain this compute into something meaningful, we have to have checks that the meaningfulness or like chaining was done correctly. So in particular here, we had to have this check that from going from step 1 to 2 to 3 to 4, we preserve the output of step 2. Otherwise, this does not mean anything. So the question was, is this like node also outputting what its snarks look like, the shape of the snarks, right? So the answer is no. So what we're going to do here is that we're constructing this f dash function using these. So this f dash will be the same shape across the things. It would just be the case it would have like if conditions. So it would have an if condition. If this is a base case, then you would run all of these checks. If it's an internal node, you run all of those checks. So here we're okay. So I think the part of the confusion comes from me not defining what f dash is doing. So what f dash is doing is that it's a claim about some range of steps, and we're going to maintain the shape of f dash across all nodes. And that is why we have to like do this special casing. Okay, if it's a base case, I want to add these checks. If not, I want to add those checks. Yes, so this is a great question. The rough answer to the question was, how many bits of security do we lose each time we do folding? And the rough answer to this is we know that we can do up to a constant number, a large constant. How big that constant is unknown. And this is true for Plonky 2. This is true for every other recursion scheme in the world, which has like, some low depth circuit for hashing. This is not a special case for, Nova or anyone else. It's just like a generic. So I think there was some Twitter thread I saw about this question. Can you define what this constant is? And the answer people were converging to is no. So we assume it's larger than any number of recursion steps we will ever do. Right. So some pretty summary here was in the case of the sequential, we were only verifying one instance of the R1CS object. And in this, we were verifying 2 of them. Is that accurate? Right. So it's slightly more subtle. So in the first case, we were only folding one instance of the run with the n instance of the run. Here, both of them are like different length as well. That does not make a huge difference for the folding itself, but it is something to note. So we had, this thing before, going back to this diagram, it was the case that we had this running instance capital UI, and we were just like shoving more things into it at each step. Now it is the case that we start with 2 both meaningful objects by themselves and shove them into one larger or double the size object. Yeah. So there's the next step that we'll get into that. Cool. Yeah, so we're pretty short on time. So now let's just skip questions for now and come back to them after this session. Okay, so quickly, first, let's define now the more interesting object that we all wanted, which is non-uniform IVC. Non-uniform IVC, I think, is basically just a way to say a VM, but with IVC. So in particular, the difference from the previous IVC slides that we had is that at each step, instead of running the same f, this f function can vary. The particular way it can vary is that it'll be some opcode of like a fixed instruction set. So one imagination could be this is EVM, and it's like add, mul, whatever different opcodes you have, and at each step you will pick the new opcode. And this opcode is picked from whatever the public input you're tracking. It doesn't have to be, but let's just assume it is. Let's see. I will not go into too much detail about what the Nova approach is, but roughly you can imagine your function f can just add like a bunch of switch case conditions, right? And in that case, the cost of this circuit would just be the cost of doing the sum of these opcodes, which I just written down as n times c times l, where c is the number of constraints per opcode, l is number of opcodes, and then it is the case that we have this other idea called supernova, which is able to do this in n times c plus l, which is a pretty big improvement, because now your multiplier of like however many opcodes you have is just gone. So in regular cases, this is like number of opcodes is like order of tens of opcodes. So this is like in one way, this is like a prover improvement of 10x, which is very nice. Right, the question is, what is the cost we pay for it? And yes, that's the thing we'll get into in the next slide. And for now, I'll just ask, please hold questions because we're short on time. Okay, so, let's see. So the key idea of supernova is that if we are doing foldings cost the size of the number of constraints. So if we know already that we have a bunch of opcodes for a VM, it is the case that they're almost independent of each other in constraints in particular. So if you have, instead of saying you have this mega circuit of all of these opcodes, you have mini circuits of each of the opcodes. And when you do folding, you add this extra, or each time you fold to only the instance of that opcode is the thing that would happen. So imagine, in this circuit or in this diagram, you had op1 or op z0 had its own circuit or circuitry, and then op z1 had its own box of folding running instance. So that is what I tried to depict here. I'll not go into too much detail, but roughly the same kind of thing is happening. It is just the case that it is repeated many times. And the one thing that you do need to do now that you didn't need to do before is that you have to prove that you're folding to the right instance. So this box says that, okay, you had option for 5 opcodes, add, mul, whatever, right? If I see a add opcode for this ith step, I should fold into the box or the UI instance, capital UI instance, that corresponds to add opcodes. So if you add this check, and this check is relatively cheap to add, then you're able to do this folding at each step at only the cost of running that opcode only. So if the add was n constraints, you're only paying n constraints, and you're not paying also the constraints of mul or whatever else. Cool. Now I will definitely not go into this, but I will claim you can also do the parallelization for this. Yeah, cool. But the part that I do really want to get into is the sort of tooling and application surface area for this. Nova has an implementation in Rust, which is very nicely written. It uses Bellman under the hood and many other things that are useful to know. The only most interesting part to know is that because Nova, or because we saw previously that the only operation you were doing is take a scalar times a vector plus add some other thing. These are MSMs. And you never have in this whole slides, you have never done FFTs at all. Because you're only doing MSMs, they're much more parallelizable. you're much less restricted to what field you're choosing. A lot of things open up. And one thing that's very interesting to note about this implementation in particular is that this uses a GPU prover for the MSMs, or GPU runner for the MSMs. So that also means that compared to like Halo 2 or something, who don't use MSMs on GPU, Nova's MSMs are like, I forget the exact magnitude, but on my Mac, they were like 5x faster. Yeah, so that means that if you already have some interesting compute that you want to try out, it might be the case that it's already faster because of this MSM being on GPU. Right. The other interesting part to note is that we were working only with R1CS constraints, which very luckily enough, we had GROT16 previously that worked with R1CS constraints. So that meant that CIRCOM, which is like possibly the most popular ZK programming language, works just out of the box with Nova. So there is this tool called Nova Scotia that will take any CIRCOM circuits and just run them through Nova. You can look at this code later. I will not go into too much detail, but the sort of to give some examples of like what prover time might look like. If you try to prove a Bitcoin block, which is about 150,000 constraints, it costs. This table is in particular for proving 120 blocks of Bitcoin. So this is about 18 million constraints if I'm doing the math right. So 18 million constraints cost about 40 seconds on my laptop, which is, I don't think I've seen anything better than that. Cool. And then the other interesting project to also note is a project from Filecoin called Lurk. They're trying to make a nice Lisp VM for doing this Nova kind of compute. They don't have Nova or any other support yet, but that is in their roadmap. Yeah, the other interesting thing to note is that all of these tooling work at the level of these step circuits. So the recursion is, cracking through this IVC, and these functions are being written in CIRCOM or Lisp or whatever else it is. The first application that's interesting to note is a VDF project. So VDFs are these verifiable delay functions, which are basically these hard to compute functions repeated many, many times. This structure repeated many, many times is basically what you look for when you're looking for applications of Nova, right? This is repeated many, many times. This is an IVC. I can just convert this F into my VDF F function into a R1CS format, and then I just chain this with Nova. So this is why the VDF project is interesting, and Filecoin and Ethereum Foundation are collaborating on getting the min-root VDF via Nova proofs. The other interesting application to note is signature aggregation. So this is basically like unlocking, the properties VLS has for any other signature scheme. So in particular, for instance, for ECDSA, if you're able to aggregate many of these, you're able to verify them in R1CS basically. You're able to do signature aggregation. And in particular, Nova has some nice properties that lend itself very nicely to being a general signature aggregation scheme. And those properties are, so one, it doesn't require FFTs or anything, so it has no constraints on, this curve needs to have some so-and-so duodicity or something. Two, it doesn't, it's only MSMs, and it's transparent and all of those things. So because of those reasons, you can work with almost any curve that exists. For instance, if you have ECDSA SecP signatures like Ethereum or something, luckily we have a cycle with SecQ, so you can work with the SecP SecQ cycle, work in right field arithmetic, and you pay I forget I know the exact numbers, but you pay very few constraints per signature verification. Okay, so those are the I think more cool general things that unlock. There are some interesting projects that use Nova. So one is from one of our friends, Liron, and a couple other people at HackLodge doing ZKML using Nova. The cool part about this project is that they're verifying 512-layer CNN in, I believe, 40 minutes or something in total. or the rough calculation comes out to they're doing 1 layer per 30 seconds, or on that magnitude of order. So in total, they're verifying about 1 billion constraints. And as far as I know, that is more than any other ZKML project. So they definitely win on that. Cool. Oh yeah, and then there's a very recent project, or a project that people here are working on, which is the ZKVM/ZKWASM group. And they have been convinced to switch to Nova as well, from a few ideas. Many of these are the ideas like, how can we parallelize proving? How can we get really efficient state representation? And for instance, one thing to note is that so far the VMs that exist in this like lookup-centric world are much less like IVC than these VMs. So the optimization surface is quite different. And also it is the case that with the structures that Supernova gives you, you can also start doing some other very interesting compiler level optimizations almost. I will not go into much detail about these either. Yeah. And yeah, I just wanted to mention that there are some upcoming features. I don't think we have time for discussion, but there's, Sangria, which is this construction from geometry, which originally just takes, I guess, the Planck copy constraints and all of the Planck constraints and converts them into something compatible with the folding scheme. And then you're able to do the same IVC machinery for Planck. But recently, they have also figured out a way to do higher degree gates, more than just R1CS. Which could lead to very interesting Planck-based constructions. Similarly, idea of lookups. Halo 2 has a nice lookup argument, which is very similar to the original Planck things. So you can also do Sangria-like things with Halo 2 lookup setup. And I believe some folks here are working on it. The other interesting ideas are, for instance, in-circuit randomness. If you have in-circuit randomness, you can do the lookups and all these things at app level instead of in the prover level kind of thing. And this is also very helpful for instance, for ZKML projects or a lot of other use cases. And oh yeah, the last one I wanted to question mark was lattices. So one idea that I tried to float around before, but never gotten a good answer for is this. Let me full screen this. So when we were running this folding scheme verifier, the reason we're not able to do the full check of A, B, C times all of these things, and we have to restrict to this folding, is because we don't want to enter this multiplicative homomorphism world. So as soon as, if imagine, for a minute that we're in FHE land and we are okay with doing multiplications for both additive and multiplicative homomorphisms for things, then it becomes the case that your verifier becomes a verifier of some lattice equation, which is likely going to be more expensive than what we're doing now, but it is still an interesting idea to explore. Yeah, so there's a more theory side idea that I just wanted to mention while we're here. Okay, yeah, that is all.